Welcome to 3 Inquisitive Kids. In this video, we will be going over what logarithms are and learn about its properties. So first, what are logarithms? Well, logarithms stems off from what exponents are. A to the power of x is equal to n. In this case, our base, a, has to be positive, and it cannot be equal to 1. Now, we can use this format to find the value of a number raised to a power. But what if we wanted to find what exponent we used to get from a number to another? This is where logarithms come in. When we write a logarithm, we are isolating the exponent, in this case x, on one side of the equation. The other side of the equation can be written as log base of a, n. In this case, n is called the argument. And a, just like in exponential form, is still called the base. So x is equal to the log of n base a. Right now we're saying that the base is positive. In any case, n would also have to be positive. So we can make a note to ourselves that n is greater than 0 if we are following these conditions. Two of the most common types of logarithms are these two shown below. This first one is called the common logarithm. This is when you have a, or the base, be equal to 10. For example, if we had log base 10 of 100, the answer to this would be 2, because 10 to the power of 2 gives us 100. Now, another logarithm is when you have the transcendental number e as our base. This is what we call the natural log. We can denote it as ln and then the argument. And for the common log, we can shorten our way of writing it to be lg and then the argument. Now that we have been introduced to what logarithms are, let's learn about some of its properties. The first property is the zero rule. We can understand this easily if we rewrite it in terms of exponential form. If we take n, a number, to the power of 0, we would always get 1. So this first rule is fairly easy to comprehend. Now, what about our second rule? If you take any number and raise it to the power of 1, you are still left with that number. Now, how does the third one work? Well, if we take the base, raise it to the value of the argument, this indeed gives us a to the power of n. Now, what if we have a number raised to a log? So let's call this property 4. We can let x be the name of log base a, n. So a to the power of x will give us n if we rewrite this logarithm in exponential form. Now, we can rewrite x as log base a of n. This is equal to n. So look, we have proved our property. Now, what about our fifth property? This is called the product rule, and it has a lot to do with the properties of exponents. So we can let a raised to the power of little m be equal to big M, and a raised to the power of little n be equal to big N. This way, we can rewrite log base a of m as little m, and same for the second term. Now, when we have a to the power of m times a to the power of n, we get a to the power of m plus n. And when we multiply a to the n power times a to the n power, this is the same thing as big M times big N. So these two values are the same. Now when we only focus on the exponents, on the left, since the base is both a's, we can combine the exponents. M plus n is equal to m plus n here. But this m plus n can be expressed in the form of log base a of mn. And these small m and small n on the left side can be rewritten as what we have here. Log base a of big M plus log base a of big N is equal to log base a of mn. And this is how we prove our product rule. And for the quotient rule, it's the same way to prove. It's just that we have turned this addition sign in the middle and the multiplication into subtraction and division respectively. You can try to prove property 6 by yourself and to test your own understanding. Now, property 7 is not really a property, but it's very useful sometimes in a lot of problems. When we have the common log of 2 plus the common log of 5, we get 1. We can apply our product rule. We would get the common log of 10. Now, because it's common log, this is actually having a base of 10. And using our identity rule, we can know that the common log of 10 is equal to 1. So, the common log of 2 plus the common log of 5 is equal to 1. Now, what about the power rule? How can we prove that? As you can see, we are taking the exponent in the argument and putting it in front of the rest of the log to make it multiplied with the rest of the log. We can let x be the name of log base a of m. So when we rewrite this in exponential form, it would be a to the x power is equal to m. And so if we have m to the nth power, we can rewrite this in terms of a to the x times n power. Now we're going to take the log of both sides. We're going to use log a. Log base a of m to the nth power is equal to the log base a to the x times nth power. So using property number 3, we can see that the right side of the equation is equal to just xn. So log base a and to the nth power is equal to xn. And what is x? Well, we have defined x as log base a of m. So our equation can finally be rewritten as this. And as you can see, we have proven property number 8. Now let's move on to the change of base rule. This is property number 9. First, we can let x be the name of log base a of n, and y be the name of log base m of a. Now let's rewrite these equations in exponential form. A to the power of x is equal to n, and m to the power of y is equal to a. So n is equal to m to the power of x times y. We have substituted m to the power of y into the a. So now let's rewrite this using log. Log base of m of n is equal to xy. This log base of mn shows up as our numerator here. So our numerator is equal to xy. And the denominator, we have log base of m base m of a. That's what we defined as y. So then the left side, indeed, is x. X is equal to xy over y. This is how we have proven property number 9, the change of base rule. And the change of base rule is very helpful in a lot of problems because you can take any sort of log and make it the ratio between two logs, and you can give these two logs any base you want. So like this is an example. We have one more property. Log base a to the nth power of b to the nth power is equal to m divided by n times log base a of b. How can we prove this? We can let log base of a to the nth power of the b to the nth power be called x. So when we rewrite this in exponential form, we have a to the n times x power is equal to b to the nth power. Now let's isolate the b. A to the n times x over m power is equal to b. So now let's rewrite this equation in log form. Log base a of b is equal to n times x over m. We can isolate the x. M over n times log base a of b is equal to x. But remember, x we defined it earlier as this. And there we go. We have proven the 10th property. Now that we've learned what logarithms are, common types of logarithms, and its properties, we are ready to do some practice problems. Here is our first problem. We are given that the function log base 4 of 4 to the x power plus 1 plus kx is an even function. We are trying to find what k is. And k is a real number. What do we know about even functions? Well, a function is even if f of x is equal to f of negative x. This is what even means. And if we look on a graph, here's a better way for you to understand it. If you have x, this is negative x, they will produce the same y value. So it would be some sort of a symmetrical graph. So for example, if we had this function, imagine if it's symmetrical about the y-axis, it would be even. F of x is log base 4, 4 to the x power plus 1, plus kx. And we know this is an even function. So we have to write f of negative x as well. Log base 4, 4 to the negative x power plus 1, minus kx. This equation should stand true. Now we can combine these logarithms. As you can see, we have shifted our terms to one side of the equation. Using our division property in logarithms, we can rewrite these two terms as log base 4. We have 4 to the x power plus 1 as the numerator, and on the bottom we have 4 to the negative x power plus 1. So plus 2kx is equal to 0. We have this 4 to the negative x power in the denominator, and that's a little bit strange. So what we can do is multiply 4x on the top and bottom of this fraction. If we do that, we would get 4 to the x power times 4 to the x power plus 1 over 4 to the power of x plus 1. As you can see, we can do some canceling. So on the top and bottom, we can cancel out the 4 to the x power plus 1. So we're left with log base 4, 4 to the x power, plus 2kx is equal to 0. Now, using our properties from before, if the base of the logarithm and the base of the argument are the same, then the answer, the value, is just the exponent of the argument. So we have x plus 2kx is equal to 0. So x times 2k plus 1 is equal to 0, which means that 2k plus 1 must be 0 itself. So when we isolate the k, we get negative 1/2. And indeed, negative 1/2 is a real number. So k is equal to negative 1/2 is our answer. We're trying to find the value of 4 raised to the power of this complicated exponent. Well, first, how can we use up this 1/2? Well, we can think of this entire thing as 4 to the power of 1/2 to the power of this complicated exponent. So this is the same thing as taking the square root of 4, which is 2. We have 2 to the power of log base 3, 9, minus log base 2, 5. And using what we know about the properties of exponents, this is the same thing as log 2 to the power of log base 3 of 9 divided by 2 to the power of log base 2, 5. Now, log base 3 of 9. This is essentially saying 3 raised to what power gives us 9? Well, of course, 3 raised to the power of 2 gives us 9. So x is equal to 2. So we have 2 to the power of 2 divided by 2 to the power of log base 2, 5. Now, using one of our properties, our answer would just be the argument of this exponent, which in this case is x. So we are left with 4 over 5, and that is our answer. Now let's move on to the next one. We have these two binomials being multiplied together. Well, many times, if we want to perform calculations with logarithms, we have to make sure they have the same base. And when we look at the bases of the logarithms in each of these pairs, we can see that they can both be written as 2 to the power of something or 3 to the power of something. So we can use our 10th property, which is log base of a to the nth power is equal to m over n log base a of b. For example, we can rewrite log base 4 of 3 as log base 2 to the second power of 3 to the first power. We're trying to get it in the format of this. Now we can go ahead and apply our property. Our first term, we will be left with 1/2 times log base of 2, 3, plus 1/3 times log base 2, 3. And in our second parentheses, we have log base 3, 2, plus 3/2 log base 3, 2. Now, because we have like terms in the parentheses, we can combine them. We are left with 5 over 6 times log base 2 of 3 times our second parentheses, which we can also combine like terms. We are left with 5 over 2 times log base 3, 2. And when we simplify, we're left with 25 over 12 times these products. But how can we simplify this? Multiplying these two is the same thing as saying, if we use the change of base formula, log 3 over log 2 times log 2 over log 3. As you can see, this just gives us 1. So our final answer is 25 over 12.